Okay, last time we finished by proving the following statement about fundamental groups. So X and Y are a pair of fast connected logical spaces, and we showed that there is a canonical isomorphism of a fundamental group of a product to a product of fundamental groups. So of course we can choose some particular fixed point here, fixed base point here, and here the corresponding base point will be a pair of those base points. Okay, so this automatically allows us to compute fundamental groups of products of spaces for which we already know. For example, if I want to put a fundamental group for two torus, which we know this one times this one, so this is isomorphic z squared. Okay. So now we will continue to study the properties of the fundamental group, which will allow us, in particular, they will allow us to calculate fundamental groups for other examples. So we want to study how the fundamental groups behaves on maps between different, with respect to maps between different logical spaces. So suppose we have a map from X to Y, and so fix some points as usual. We fix some base point in X, X0, and its image, let's call it Y0. And so this is the definition. Then we can consider the following map, which we will denote by phi star. The map from y1 x with base point x0 to y1 of x, so of y with base point y0, which is the image of x0 under phi, so that is explicitly defined as well. So if I take a class of a loop in my space X, it is sent to a class of a composition with my function map f, which defines loop, and continuous map phi. So such map is called push forward, or sometimes induced homomorphism. Of phi. So why it's a push forward? So it's the grammatically one can say the following thing. So we have a map. So phi, the path can be understood as a map from unit interval to x, and so there is the following commutative diagram. So we can compose it with the map phi from x to y, and or we can go directly here by composing. So of course, since f was a loop, so the composition with some continuous map phi will also be a loop here, and this kind of pushes, I can set this map, this kind of map phi pushes forward in the same direction. The loop have induced map star in these guys. So again, a few remarks in order. So as usual, since we define this map by choosing some particular representative of an equivalence class, this is well defined actually. So because if I take some other path in X, which is path homotopic to my path F, then so suppose there is some homotopy F, path homotopy F. And then I can compose this realizes me path homotopy between the following compositions. I just can use here the path homotopy, which is a composition of my homotopy here. Path homotopy here is my map. And then it follows that phi star, by definition of my phi star, indeed phi star of a class of F is the same as phi star of a class of F. And the second remark, it's a homomorphism, which justifies this main inverse homomorphism. So we want to say that this respects group structure here and here. Namely, if I take, so I need to check if I take product of elements here, so product of two classes here, F and J, it will be mapped to a product of corresponding images in this group. So first I use by definition the product structure here. This is the same class of the composition of paths F and G, and so by my map phi star, it is mapped to a composition of phi. This composed maps F and G. So this is a composition of functions. This is a composition of paths. But of course, just by definition of the composition of paths, and this is the same as first. This directly follows from the definition of this composition. This is the same as composition of F composed with phi, and the paths obtained by composition of G with phi. This is indeed, by definition of the product here, this is indeed the product. This classes, which is same as phi star acting on F, and phi star acting on H. So it has the following nice properties. First property, suppose phi is the identity map acting on X. This implies that the corresponding push forward is identity acting on fundamental group of X. So this immediately follows from the definition, because the composition of this identity does nothing. And second property which we want to show is that if I take a composition of some maps. This is the same as a composition of the, and take push forward is the same as taking a composition of the corresponding push forwards. So this requires a bit of elaboration. But this also more or less follows directly from the definition. So what happens is the following. So I have a triple, now I want to consider a triple of topological spaces. So I start with some topological space X, and then there is a map from phi from X to Y as before, but then there are also a map from Y to say Z, which we call psi, and I consider paths F and X, and then it's with phi is pushed to the path in Y, which is a composition of phi with F, and then I can first compose this path with psi. But of course I can, since this composition is, convert the order of the composition is the same as just this function is the same as the function obtained by first composing psi and phi, and then composing it with the path of F. So this means you can go directly like this and continue with this composition. And of course I need to fix, I need to fix some base point in X. This goes maps to some base point in Y0, and this maps to some base point in Z. And all those guys, they induce the following maps between the corresponding fundamental groups. Star, or can go directly by considering the composition, and going this way directly, or composing this push forward is the same just because of this property and the definition of the push forward. So this. Questions? So for those who are familiar with category theory, let me make the following remark. So these properties mean that phi1 is a functor from the category of topological spaces. So the category of groups. So in this category, the objects are topological spaces, and the morphisms are continuous maps. And in this category, the objects are groups, and morphisms are homomorphisms. But if you don't have category theory, you can just see. So now we want to to show the following proposition. So suppose R is a retract of X, topological space A, X onto its subspace X. In particular, we can have in mind the following diagram. So there's a map from X to A, and R, as we know, as R is such map that if I restrict R on A, this is identity on A, and they also have a map. So this is the inclusion map, or we can go. So this is a comparison. Okay. And then, in this situation, so you consider the push forward of the inclusion is a map from pi1 A of x0. So this is some point which I fix in A, but A is also A is considered a subspace in X, so this is also point can be treated as a point in X. So map. So I here induces a map like this, and the statement that this is injection. The first part is the proposition, and the second part is the situation. So if there is a stronger condition, it's not just the tag, but the condition that X deformation retracts onto A, then I star is an isomorphism. In particular, this statement allows us to say something like if you know how to retract X to some subspace, and we can say something about fundamental group of this subspace. This gives us some information about fundamental group of the original space. Okay, so how do we prove this? The first part is pretty easy. We just use the properties which you showed before. So R is retract. So we know that R is a retract, and we know in particular that so this statement that the restriction of R on A is identity on A is equal to the statement that if I do this composition, first inclusion and then R is the same as identity. Just rewriting this condition. And then by the properties of the push forward, I have the following condition. This is the composition of the corresponding push forwards is identity on the fundamental group. But it's only possible if I have the composition of two maps being identity. It's only possible that if the first map is injected. So now we have a stronger condition. This is a deformation of a track. So this means, by definition, there exists a homotopy f x times interval for x, such that the homotopy between identity on x and the composition of maps I and R in this order. This is a map from x to x. Okay, now so we already showed that the I star is injective, so it's enough to show that it's surjective. In particular, we need just to show that any loop inside A can be represented as an image of I star. So okay, let me take any loop. So to do this, take any loop F inside X. I want to show that its class is I star of something. This will show that I star is surjective. And to do this, we notice that because of this, we have this homotopy between identity and this composition. If I compose this big F with my pass F, small f here, this gives me a homotopy between these two paths. And so I can understand this composition as a pass, A. And it follows it by definition of the push-forward map. So if I take a class, pass homotopy class of both sides of this equivalence relation, I get that this is I star of class R. And indeed, so for this was possible to do for any loop X, and this means indeed that I star is subjective. And if I first use the result thing here, this means I star is an isomorphism. Questions?
Yes, in the first proof, if we exchange I and R, we get.
Well, there is no statement that this is just identity, but there is a statement this is homotopic to identity. So we cannot use directly this, but we have to use this kind of together with the homotopy. Any other questions? In particular, for example, we had this in the very beginning. We have this example of homotopy deformation retractions of, for example, analogous to a circle. So this immediately implies that the fundamental group of an anomalous is the same as the fundamental group of a circle, which is that. But there is actually a more general statement in the following. Suppose phi mapped from x to y is a homotopic equivalence. Within the topological spaces x and y, then phi star is push forward, which is a map by 1 of x to pi 1 y phi of 0 is an isomorphism. Essentially, the second part of the first proposition, of the previous proposition, was a particular case of this more general statement, because we know that the deformation reduction, if we have deformation reduction, this we have a homotopic equivalence between x and its corresponding subspace. So before proving this, we will prove the following lemma. Maybe not space. Okay, so I fix some point x0 and x, and that phi be a homotopy of maps from x to y. So the homotopy between functions phi 0 and phi 1. So these are just restrictions of this to 0 and 1, which I will denote just at 0 and f1, and maps x to y. So this is the same as just restriction, but I want to have condensed notation. And let me define H to be a map from unit interval to y, such that it sends S to phi of x0, my point fixed here, comma S. So I can descend this H. This is a path in y from let's see, so the from phi 0 of x0 to phi 1. And so then the statement is the following. So I have two maps from x and y, and for each of them I can consider push forward. Question? So push forward of phi 0 sends this fundamental group to the fundamental group of y, with base point being phi 0 of x0, and push forward of phi 1 sends it to fundamental group of y, with base point being phi 1 of at 0. But we also constructed, previously we constructed a map between, so if you consider two fundamental groups with different base points in the same topological space, and there is a path connecting these 2 points, and this is the case for us, and then if you consider the corresponding, the path connected to 2 base points, which we know by H, and then there is one can construct a homomorphism beta H between these fundamental groups, and this actually will be isomorphism. So this is this BH is what we constructed previously in the lectures for a given path H, and the statement is this diagram is commutative. How do we prove this lemma? So we need to show essentially that this map is a composition of these maps. So we take some probe to do this. Let me take some probe paths in X, and we need to show that we need to check if I apply phi 1 star to F the same as the application of this composition on F. Let's see, need to check. Of course, this should be a path starting and ending at my fixed base point. 0. Okay. So I can draw some picture. So that's some X, logical space X here, so I have some paths. F, that's the map from X. So actually, the family of maps from X to Y, parameterized by unit interval. And so I can consider in particular a map, the image. So what happens if I apply phi 0? So this is so the looped map to composition phi 0 is F. But I can also apply phi 1 and it will be mapped to some other loop starting at phi 1 and 0, and the loop itself is a composition of phi 1 with F, and I also have a path H between those 2 points, which is just defined using my homotopy phi. So I need to check the statements, or just, so let me first use the definition of all these homomorphisms, acting on the fundamental group. So by definition, the left-hand side, I want to check the class of one of f is the same as class of the following. So I should apply the following composition. So if I first apply phi 0, so this is just to take a composition phi 0 with f, and to apply this BH, I need to compose it with h on the left and h bar, the inverse part on the right, and I have to take this class. So of course, to check that the classes are the same, it's enough. This is equivalent to check that these two paths are homotopic to each other. There is some path homotopy f, which relates these guys. So the left-hand side is just this path here, and the right-hand side, what is this? So I go. So it's a path homotopy of paths with this base point. So left-hand side is just this path, and the right-hand side is the following loop. I go along arch in opposite directions, and I go along this loop, and then I return. And of course, so geometrically, how do I construct this homotopy? Is just I use my original I use my homotopy phi. So I use kind of if I have a family of, consider a family of my maps from x to y, and so if I take some particular point t in my interval, I consider the composition of this phi restricted to this point is f, and it will be again some loop. And once I vary t from 0 to 1, this loop deforms from this guy to this guy. I also have to take into account I have to simultaneously, to understand the path homotopy of loops starting at this point, I also have to deform this path h, so that I have to contract it once I vary t from 0 to 1. So this is what happens geometrically, but one can just give so what is the explicit path homotopy, expression for path homotopy which realizes this geometric picture. We take the following ht. So ht will be a path, kind of a truncated path which goes like this. So this point is phi of x0 t, so it moves when I change t from 0 to 1. And so then this is this path in the middle, and then compose it with ht bar, and explicitly ht, the path ht is defined by the following, can be defined by the following function explicitly: s plus t minus ts. So this is a path from phi x0 t to phi 1 of x0. Mistake, we can check this indeed true. So there is some change of variables which realizes this truncation. Okay, so yeah, so this this shows that this provides the example of such a path homotopy, and this proves the lemma. So we showed these guys are identical for any loop. Questions? And this requires some work, but I mean, geometrically, the picture is just like you just deform this pass. Loop to another, and you shrink this pass. Okay, so now we are ready to prove the proposition. So the proposition was the statement that the homotopy equivalence, the push forward of homotopy equivalence is an isomorphism. Okay, so phi my homotopy equivalence. So what does this mean by definition? It means that there exists psi map in the opposite direction such that it's a homotopy inverse to phi, which means that this composition is homotopic to identity on y, and this composition is homotopic to identity on x. Okay, so to be more careful, so let me consider, so what is the, we want to consider induced maps for phi and psi, but we have to be careful, so in order to define induced maps, we also have to fix base points. So let me fix some base point x0 and x. Let me start with phi 1 of x and x0, so I can apply induced map of phi like this. So it will map to phi 1 y phi of x0. Then I can apply well, let's psi star, but it will be homomorphism to phi 1 of x, this base point, not the original one, but psi composed with phi. It's not just acts back. And I can also apply again to this guy, apply push forward for phi, but I want to distinguish this push forward from this push forward because it starts on a fundamental group with a different base point. So this is why I use prime here. Phi of psi. So this is my situation. How the corresponding push forwards work. Because there might be some value in my situation, this is actually x0. It's not true. So first, so I can use my lemma in the following manner. So this is this composition is homotopic to identity. But then we in the lemma we showed that this is this means that this. So in the lemma we showed that if the two maps are homotopic, their push forwards differ by this map beta h which we defined. But we also showed that the beta h is isomorphism. So this means that if I take the push forward of the left-hand side, it will be an identity up to an isomorphism. So we still have the statement this is an isomorphism. From lemma it follows that phi, the corresponding push forward, which we already know that the push forward is a composition of the push forward is a composition of push forward is an isomorphism. Because it's a composition of beta for some path h with identity, with the push forward of identity which is identity. And then it follows, so if such composition is an isomorphism, this only can be true if psi star is injective. Otherwise, this composition cannot be an isomorphism. So let me apply lemma. Now apply lemma to this guy. And now I will use the corresponding composition of push forwards will be this composed with this. So there will be similarly. Sorry, what? Sorry, yeah, before. No, actually before. If you wanted to apply this, this was practical, right? So if you want to compose this and this. And yeah, so if you now want to apply lemma to this, this will be this composed with this. But it was important the map side, so although this push forwards are different, this is the same guy. This is an isomorphism, and now, from this it follows that the psi star is surjective. Okay, now psi star is both surjective and injective, and this means that psi star is an isomorphism. But then, of course, if this is composition is an isomorphism, then also phi star is an isomorphism. Questions?
Yes, I have a question, but it's more in topology in general. So if we have true topological space, is it true that one should always be isomorphic to a subspace of the other one?
What? I don't understand the question.
So if we have true topological space, is it true that one should always be...
What's the relation between these two spaces?
No relation.
Yes? Then?
No, I don't think this is true.
I haven't put the question.
So is it true that one is always isomorphic to a subspace of the other one?
I mean,
That's something finite, something finite.
yeah, you can pick something like this discrete topology, and the other guy to be something like an interval.
Or just as a set. I mean, even in set it's not. If we take something finite.
In set it is true.
Something finite cannot be isomorphic to a subspace.
No, I mean
One
they
of
are
them?
comparable as one of them.
some point where the inclusion star is not needed?
Inclusion is not.
The star, the inclusion
Oh.
star.
Yeah, I mean, just consider a circle and include it into R. Well, R3, for example. I mean, you know that this is Z and this is. Okay, so now we want to. Yeah, so it's promised at the very beginning. So pi1 is understood as invariant of topological spaces up to homotopy equivalence. It's the same. Of course, we automatically have invariance. So for homomorphic spaces, pi1 is the same, but we have it's a kind of a weak invariant. So it's invariant only. It depends on the homotopy type of a topological space. So all kind of continuous. I mean, you can say homotopy is some sort of continuous deformations, and which also allows kind of shrinking some stuff to points. And this is a by one can only distinguish topological spaces up to such deformations. So we kind of now we are preparing to prove to the proof of one competence theorem. And but first we will prove some sort of an easier statement, a weaker statement, but it will help us in proving one competence theorem later in particular. So we prove the following lemma, but already lemma is quite will allow us to make some to consider some other examples of the fundamental group. So let X be covered by a union of open sets A alpha, and so let me fix some point x0 in X, and we want that each of these open sets contains this point. And moreover, we want that for any alpha and beta, A alpha itself and all their pairwise intersections are path connected. Then the statement that for any loop in X, starting and ending at 0, there exist loops HI. I can understand them as loops in A alphas some index alpha I. But I can also, by including those guys into X, I can also do them as loops in X. I varies from 1 to n, some finite number, such that F is homotopic to their composition. The same is that if you have this cover with these properties, we can always, for any loop in X, it can be decomposed into a composition of loops sitting inside those subspaces. I used too much space. So how do we prove this? So if f is continuous, then for any s in the unit interval, there exists a neighborhood its neighborhood denoted by Vs, open neighborhood. And again, without also generality, we can assume that Vs is just of the form this open interval in R intersected with 0, 1. And so the fact that f is continuous, this means that for any s, there exists such neighborhood such that so I can actually require, so in principle I can, so the statement that this open neighborhood, the image of the open neighborhood is contained fully inside I alpha I, well let's say I alpha for some alpha. But if I can always reduce my interval a little bit, so I can always require not just open interval, but the closed interval to also sit inside a given a certain element, a certain subset in the cover. So now, well, we use this kind of trick which we used before in some proof, that so we use the fact that the interval is compact. And then, so this means I can always choose a final, it's a finite cover of this interval by 0, 1. Finite cover of unit interval by those open spaces satisfying this condition. Or my data formulated in the following way. So this means, so this, I can say that there exists a finite cover like this, where this only runs over some finite set. But this can be reformulated as the following statement. So this implies the following statement, that there exists a partition of the unit interval by points inside whatever points as 0, S1, and so on to Sn. Well, Sn minus 1, and then Sn, the same as 1, such that for any I, the image of the closed interval connecting two neighboring points with this partition is inside A alpha I for some alpha I. So how, for example, I go from this statement, from this finite cover to this, I just take, for example, these points as the partitions to be union of all endpoints, all possible endpoints, AS and BS, which appear in this finite union. Okay, and okay, so now we so far we only used essentially the properties of the fact that the f is continuous function, and we had some cover, some open cover of my topological space X, but now we need to use the further properties, further constraints on this cover. So in particular, we have this constraint that any pair, the intersection of any pair of these open sets in the cover is path connected. And in particular, the intersection of these two guys is path connected. And we also know, in the condition of the lemma, we had that each of these open sets contained my base point x0, and this means, since this is path connected, there exists a path G, well, Gi, the path in X, but I can require, since this is a path starting, this path in X, starting, well, this is a path, let me say it this way, from X0 to F of Si. So both of these points, by this construction, both of these points, both of these guys also contain F of Si from this property, and so the path connected. So I can always find a path between these pair of points, which lies, whose image lies inside this intersection. So the image of G is inside this intersection. So let me denote by Fi to be a part of the pass F from F of Si to F of Si plus 1. So in particular, I can use the following explicit parameterization: Fi of S. So Fi is a new pass in X. So it's a pass connecting these 2 points, which are images, like images of the endpoints of this interval here. And I can use, for example, defining explicitly this, for example.
Plus 1, Si plus 1.
Oh, yes. So what is the picture of this ratio? So it's ontological space X. So there is an endpoint x0. There's some big pass, regional pass F, and so what we did. So it's parameterized by some variable S in a unit interval. And we split, so what happens, so we split this interval into n pieces. So let's, for example, this is a f of S1, this is f of S2, and a dot here, f of Sn minus 1, this is f of S minus 2 dot. And so the splitting corresponds to the splitting of my unit interval, and so this small pass denoted by F1, this small pass F2, and so on. This is sorry, this should be no. I guess everything.
The definition of the Fi is not.
It is not the wrong something.
I think the one you wrote first is. No, just put the first place. It's I. No, it's I.
So let's see. Okay, yes. When S is 0, so when S is 0, this should be S I, and yeah. This is a pass from. So F0 should be a pass from. Yeah, this should be F0. This should be F1, and this should be F n minus 1. Right? Okay. And moreover, we chose so for each endpoint we chose a pass G. We will pass G1, a pass G2 like this, and so on. So pass Gn minus 1, Gn minus 2, and so on. So we use the fact that each of these intervals, small intervals, is mapped to a particular subspace A, and moreover, for two neighboring intervals, the intersection is path connected and contains and contains also point x0, so there exists a path G2 like this, which lies completely inside the intersection, this intersection in subsets. Okay, so yeah, essentially this picture gives us the result. Let me just write the formula. So F, of course, F is homotopic to homotopy is the composition of all those guys, small paths. Again, so using path homotopy properties, I can always instead everywhere in the middle here, I can set it GI and GI bar. So I can, so here, I can set GN minus 1 and the GN minus 1 bar, and minus 1, GN minus 2. Bar. So what I'm doing here? Double dot. At the end, I have something like F. Okay, F1, G1, G1 bar, F0. Right. So let me now read it from this way. And so I go for F0, G1, then return G1 bar. So no, it's again, yeah. G1, then I go G1 bar in the opposite direction, then I return on G1, and I go like this, like this, like this. Okay. And okay, then I just, now what I use this, I denote this as H. This pass as H1, this pass is G2 here as H2. So this pass is HN. This is H1. Okay, and so this indeed provides me as a desired decomposition. So we want to require that each class H lies in some subspace alpha. This is indeed the case because by construction, what we had is that by construction, this guy Fi, each Fi, the image, it was lying in I alpha. See if it's from this one, right? And GI was lying both in alpha A alpha I and A alpha I plus 1, and then it follows that each of these guys is absolute shift each when n Hn is oh, you have to be, you have to maybe more careful to check if I already forgot what was the definition of this guy. There may be some shift by one. And I mean, this, what's important here is that this is by construction. It's obvious that each pass lies entirely in some of the open subspaces. This proves the lemma. Questions? So what can we learn, for example, from this statement? For example, the following, we can learn that the fundamental group of n-dimensional sphere is trivial for n. Well, this is kind of obvious. Well, I mean, this is kind of obvious for S2 to visualize. I mean, one can of course prove it by constructing explicitly path homotopy from any path to a constant path, but I can prove it less explicitly by using this statement. And so if you realize this is just some example of application of this lemma. So if you realize, as usual, the n-dimensional sphere as a subspace in n+1 dimensional Euclidean space, given by this condition, and then we can always cover it by just two open sets, such that A1 is we remove the north pole, and A2 we remove south pole. So of course A1, this intersection is path connected. We can apply the lemma, and we also know that I is or I1 or 2 is homomorphic to Rn, for example, by stereographic projection. So let me remark that so this is only true. The fact that it's path connected only true under this assumption. And so it's if n is 1, for example, this is not path connected. This intersection. So, for n equals 1, this is something like this, A1 and A2, and the intersection is this is not connected, so we wouldn't be able to prove this, which is consistent. Okay, and from this homomorphism, it follows that the fundamental group of each of these subspaces is trivial, but then from lemma, so each path, each loop in I alpha is contractible, and then it follows that since we know that any loop here can be represented as a composition of loops here and here, all of those, any of these loops is contractible, though any loop here is contractible. Questions?
Geometrically, I don't see how, if we remove 2 points to S2, for example, and we take the equator,
Yes.
then
Well, I mean, this is, so, okay, let's consider n equals 2. So you have S2 looks something like this. Indeed, A1 is, you remove north pole, A2 you remove south pole. So the statement that any, so if I remove, for example, so if I remove north pole, I can stereographically project on R2 like this. So this gives me the fact that any loop in A1 is contractible. If I just remove 1 point. I'm not using any statement which would be a false statement, that I remove both points, any loop is contractible. I'm just using, if I remove one of them, is contractible, and I remove other, any loop is contractible. Okay, so before formulating one compound theorem, we need to introduce some algebraic notions. I don't know, maybe if you already studied this notion or not, but in any case, let me define it. This is a notion of a pre-product of family of groups H alpha, alpha runs over some set I. And so this free product of some arbitrary family is denoted by, usually not by star. Alpha. But of course, if there just some finite number just indexed like some finite set, like this, you can use like this. So what is group? So first, let me define G as a set. So the set, so let me describe this as follows. This is a set of all words, or some of I can say formal products these words in elements of my groups HI. So what are these? So this is a this is just sequences, ordered sequences of elements so each element in the sequence belongs to some particular group in my family. And we also require that if I consider two neighbor elements, the difference between indices is 1, and then they need to belong to different groups. So this defines it as a set. Now I need to define what is a group structure. How do I multiply two words? So let me take one word and another word denoted by parent elements. So in order to define this, first what I do, I write just a word which is obtained by concatenations of these two words. But this is not the final answer which I want. So I want to perform a certain operation on this thing, which is called reduction. Reduce, I want to reduce it according to the following rule. So if somewhere in the word I encounter neighbors, pair of neighbors which belong to the same group, I change this word by replacing this pair of elements to a single element, which are obtained by multiplication of those guys in H alpha. And of course, I need, by construction, it's obvious that there are only a finite number of operations like this I need to perform to bring it to this form. So in principle, what can happen is that once I do this, these guys can happen to be from the same group. So I need to replace them by the product, and so on.
If it didn't happen to be in the same group, then
yeah, then it's
remains.
yeah, it's okay. Yeah. If those guys not the same group, then it's already good stuff. But you might need to perform this a few times because it might happen to be okay. The statement that yeah, it's important to say this is not one. It's not trivial because it might happen that once you do this, it becomes one, and those guys are also from the same group. And you need to do this. So let me give you, for example, let me give you an example. It's very simple, and we'll stop.
So if the two groups are the same, then it just becomes the same group? I mean, like if H1 is equal to H2, then
No.
H1, H2 is equal to H.
No, the free product is not the same. It's a free product of this. Okay, let me.
But here we are saying that if we take the sequence, then if G1 is in H1, then G2 need to not be in H2.
Sorry, G1.
We are saying that two consecutive elements they need to not belong to the
Yeah.
same group.
Yes.
So if they're all the same, how we will do? If they're all the same, I mean.
Sorry, what do you mean? I mean, here they're from different, not, any neighbors are from different, any pair of neighbors are from different groups.
No,
Here,
for example, just in the case of two groups, H1 and H2,
Okay.
we say if we start in G1, H1, then G2 needs to not be in G1 and H1.
yes,
Yes.
it's gonna be in
Yes. So now if we take H1 is equal to H2.
No, but this is considered to be
different copies.
different copies
Okay.
of.
Okay.
I mean, this is a different, or they may be isomorphic, but they're different groups. Okay, let me just a couple of minutes, but I want to finish this definition. Well, I mean, this definition is okay, but of course we need to, I mean, a few remarks about why it's actually a consistent definition. So it satisfies group axioms. So the unit here is a trivial word or empty. So here we allow m to be 0. And of course it's acts indeed trivially. And so second is existence of inverse, and inverse is given by just inversing the order of the elements and in the word and inversing each of them in the individual group separately. And the third is associativity. So this is left as an exercise. But this is more or less some combinatoric this reduction. I mean, so I mean, of course, this kind of this part of the definitions indeed is invariant under the way you put brackets, because it's just concatenation words. But you also need to make some arguments that this reduction procedure also independent of the order.
About the trivial word, it will be one, so a word of one in each group. Or
No, it's just M. This thing is a sequence of no elements. Is 0 elements. It's not here. We don't allow ones actually. Okay, that's it.